Hi, I'm Mike Seaman with Eta 1 Power. In this video, I'll use parameterization in Eta Designer to create a closed-loop 600-watt LLC converter. I'll use design variables to select component values and then understand the waveform timings and home in on the right converter parameters. Finally, I'll close the loop and use parameterization to quickly stabilize the converter and optimize the startup response. I'll start by opening Eta Designer. As Eta Designer does not have an LLC converter and a set of templates, I'll have to adapt the closest option, the half-bridge converter. I'll choose an input voltage from 300 volts to 400 volts, an output voltage of 12 volts, and an output current of up to 50 amps. I'll now choose the half-bridge converter as it's the closest to the LLC and can be quickly adapted. Finally, I'll choose a switching frequency of 300 kHz, as that's close to our target design point. So here's our design. I'll start by adapting this to an LLC. I'll first delete the output inductor, connecting the transformer straight to the output. I'll add an inductor on the primary side to act as our resonant inductor. The two existing capacitors will act in parallel as a resonant capacitor. I will now parameterize the resonant network in this converter. To create design variables, choose Edit Design Variables from the Simulate menu. The project comes with 3 default variables: input voltage, and output current. I'll add a few more variables. First variable will be for the resonant frequency. I'll set a default value of 300 kHz and choose linear range from 200 kHz to 400 kHz to allow later variation. Then I'll add a parameter to set the resonant inductor with a nominal value of 10 microhenry and set a logarithmic range from 4 microhenry to 40 microhenry. Finally, I'll add a parameter to capture the magnetizing inductance. This parameter will capture the ratio between the magnetizing inductance and the resonant inductance, a critical parameter of the LLC converter. I'll set that to a typical value of 4, ranging between 3 and 10. I don't need to specify the resonant capacitor here, as that's a direct function of the resonant inductor and the resonant frequency. Now, let's place these parameters into the schematic. I'll start by setting the value of the resonant inductor to LR. Now, I'll set the magnetizing inductance of the transformer to Lm over Lr, the ratio parameter I defined, times Lr to get the desired magnetizing inductance. Since the resonant capacitors are in parallel in small signal terms, each capacitor will be half of the desired value. Since the resonant frequency is 1 over 2 pi times the square root of L times C, I can solve for the needed capacitance. I'll set each capacitor to 0.5 divided by Lr times 2 pi times the resonant frequency squared. I'll copy this expression and paste it into the other capacitor's value. I'll now define the transformer turns ratio. I'll set the secondary to use 1 turn each, and then set the primary for a turns ratio of 12. I'll revisit this later once we inspect the regulation capability. Finally, I'll choose models for the primary side switches to accurately capture the switching behavior of the circuit. Now that the circuit components are defined, the controller has to be set up to drive the LLC converter in the desired way. I'll add a few parameters to set up the controller. I'll open the Design Variables dialog again. I'll add a parameter, FSW, to represent the switching frequency, close to the resonant frequency, but it can change to achieve regulation. I'll set it to a nominal 300 kHz, varying between 150 and 500 kHz. Next, I'll add a parameter to capture dead time, called dt. This variable will set the dead time between the two primary side switches. I'll set it to 0.1 microseconds and allow it to vary between 50 and 200 nanoseconds. Okay, now I'll open the controller block to define our waveforms. The waveforms are left over from the old half-bridge converter. I need to remove some constraints to allow us to adjust the waveforms as needed. I'll now remove the constraints from the SR waveforms. Then I can drag the waveform edges back and forth to rearrange them to what is needed for the LLC converter. If I remove the constraints from an edge, it can be moved freely. I'll start by defining the first pulse edge. This I'll set to the period, equal to 1 over the switching frequency. The rising edge of the second waveform is set to half of a period following the rising edge of the first waveform. You can see the constraint on the timing diagram as well. Looking at the falling edge, I'll first delete the existing constraints. Now I'll use this edge to set the dead time. So this delay will be set to half the period minus the dead time. Okay, now I'll look at the falling edge of the second waveform. I could set the same delay as from the first waveform, but this constraint is better. This constraint, left over from the half-bridge converter, will ensure this pulse has the same width as the high side pulse, ensuring symmetry. This constraint sets the dead time from the rising edge of PWM-L to equal the time from PWM-H's rising edge to its falling edge. I'll keep this constraint. Now I'll adjust the delays for the secondary side waveforms. I want these to closely match the primary side waveforms, so I'll add a short delay of 10 nanoseconds for each of the edges of the secondary side waveforms. Now that the controller is defined, we can look at the converter operation. I'll pull up the Transient Simulation window. Here's the startup waveform. It's open loop, so the response is not well controlled yet. I'll add the 4 gate waveforms to the bottom plot by selecting the plot handle, then clicking on the probe tool, and selecting the 4 gate waveforms on the schematic. I'll press Escape on the keyboard to exit this mode. As you can see, the secondary gate waveforms match the corresponding primary waveforms closely, and there is a short dead time between pulses. If I zoom in to the primary side waveform, we can see the dead time is sufficient to achieve soft switching on the primary side. I can now sweep the design variables by selecting Sweep Variables to see the converter waveforms vary accordingly. I can vary the input voltage down and up to see the output voltage change in response. I can also vary the output current from light load to heavy load and see the open loop response. I can then vary the control variables, for example, switching frequency. If I switch faster, the output voltage drops as expected from the LLC characteristics. If I switch slower, the output voltage increases, but starts to get spikes on it. Let's examine what's happening here in more detail. I'll start by changing the color of the primary side current to red, moving it to the first plot by dragging its name, so it's with all the other primary side traces. I'll then add the 2 transformer secondary currents to the second plot. Let's zoom in and see what's happening. At switching frequencies below resonance, the secondary side currents actually reverse and send energy back to the primary side. This will cause switching loss and additional circulating currents, so we want to avoid this. Let's look at how this effect shows up. At higher switching frequencies, the secondary waveforms look fine, but at longer periods, the reverse current starts to show up. I want to change the controller to prevent secondary side pulses from exceeding the maximum value. I'll add a new design variable called tsrmax as the maximum SR on time and set it to 2 microseconds with a range from 0.5 to 3 microseconds. Now I'll add this parameter to the controller. I'll modify the falling edges of the synchronous rectifiers. The initial dead time constraint is okay, but I'll add another constraint and use OR logic to trigger this edge at the first of the two constraints. I'll set this to a delay of tsrmax from SR2's rising edge. I'll add the same constraint to the other secondary waveform, SR1. I'll go back to the waveform and adjust the delay value. We still see that we have reverse currents flowing, so I'll adjust tsrmax down until, just like that, the reverse currents disappear. Now we have nice looking waveforms at low switching frequencies. I can now save this value of tsrmax to the project by closing the window and then allowing Eta Designer to copy these values back to the project. I'll open the transient window again and sweep the variables to ensure that we have correct regulation range available to us. I'll set the input voltage to minimum and the output current to the maximum of 50 amps. I'll measure the output voltage when the output settles by turning on the cursors, moving them to steady state, and selecting to measure average values from the measurement menu. The output looks high, so I can go to the switching frequency variable and increase it until the output voltage reaches 12 volts. Now let's examine the other case, maximum input voltage in light load. Okay, the output voltage is quite high. Let's increase switching frequency to bring it down. I can't seem to get it low enough, even at maximum frequency. So let's modify the turns ratio. I'll go into the schematic and change the turns ratio to 14:1. Now, back in the simulation window, the results are updated automatically based on the new turns ratio. Now we can see we can meet the light-low condition. Now we need to re-examine the worst-case condition. At minimum input voltage, maximum load, we see that our output voltage is quite low. I can now reduce the switching frequency to see if we can get the desired 12 volts. And yes, it does seem like we can get to 12 volts at this frequency. So I've now verified the desired controller range can be achieved. Next, let's close the loop on this design. I'll start by going into the controller block again. I have a PWM ramp from the half-bridge converter. Let's repurpose this ramp to control the period of the waveform. I'll set the slope to the resonant frequency FR to control the controller uniformly with the converter design. I'll rename it to ramp as it's no longer controlling duty cycle or PWM. Next, let's modify the filter. This is the original compensator or filter. I don't need a PID filter for this design. A PI filter is sufficient. I'll set the minimum and maximum values of the filter to apply limits on the switching frequency as a function of the resonant frequency. I'll choose a minimum of 0.3, maximum of 0.6, and an initial value of 0.4. These can be readjusted if the control range cannot be met, but they need to keep us within the allowed operating range of the LLC converter to avoid leaving the ZBS region. I don't know what the desired control parameters should be, but I can again parameterize them. I'll set the DC gain to a variable called gain, and the 0 to FZ, and the pole to 10 times FC. I'll set up these variables later. I'll first modify the falling edge of the high side PWM. I don't want to delay anymore, I want to filter compare. I'll set this falling edge to occur when the compensator output, the loop, is less than the ramp voltage. In other words, when the ramp exceeds the error amplifier output. The constraints are already set up to ensure that the low side pulse width matches the high side. The only thing I need to do is remove the period constraint and set the rising edge to a delay of the dead time dt after the falling edge of the low side PWM. I see that there's an error, and I have to define our two controller variables. I'll set the controller gain to 10K and have it logarithmically vary from 1K to 100K. I'll then set the zero frequency, Fz, to 30K and range from 1K to 100K radians per second. Okay, the converter has started up already. Let's see where the converter is operating. It's at the worst case conditions now. I see that we have some asymmetry in the current waveforms. I don't want that. When I change the current and the voltage, the asymmetry stays and even gets worse. Something's wrong with the controller. Let's re-examine the controller to find the problem. Okay, here's the problem. The delay for the secondary side is set to half of our old period. This should instead be a dead time of dt after the high side falling edge. I'll set that now. Okay, nice. The simulation has automatically rerun and the waveforms look perfect now. The output voltage settles nicely at near 12 volts. And if I increase the current, the output voltage stays pretty fixed. At startup, you can see the converter following the desired soft start ramp. Let's look at the input voltage regulation. At low line, the output sags. Well, it has a long tail. Let's see if I can speed up the controller. I'll start by increasing the simulation time to 400 microseconds and fitting the data to the window. There's a slow tail in the output voltage, so let's fix this. I'll hide the measurements and cursors. Now I'll vary the gain and zero frequency to improve the response. I'll increase the gain and the tail goes away. Oh, it's getting a little unstable there, so I'll turn down the gain a bit. Now I'll tune the zero frequency to better damp the response. Okay, that looks good there. Okay, let's look at the variation with input voltage. As it goes up, the regulation holds output voltage pretty constant. Next, let's look at output current. As I reduce the current, the output stays right at 12 volts. It looks like our controller has a good response and tight regulation across line and load. You've seen how parameterization in Eta Designer enables users like yourself to quickly understand the operation and waveforms of a converter, and quickly get the component and timing values tuned in. These timing variables are also critical to quickly stabilize closed-loop converters and to tune the transient response. I hope you've enjoyed this video and have learned how to use parameterization in Eta Designer to quickly tune converters, open-loop controllers, and closed-loop compensators. Please check us out at etadesigner.com to download a trial version and to view more instructional videos like this one. Thanks.